John Hildebrand.
Hello, and thank you, and welcome to my webinar. Just a quick background on myself. I work as the Business Development Manager for Belimo. I've been with the company about 15 years, most of that time spent with the sales organization. We've developed this presentation as a way to describe some of the causes and consequences of low delta T syndrome, not only in the building, but also how it can impact and affect our environment as well. First, we'll take a look at the role buildings play in the environment. The Paris Agreement, signed into international law in November of 2016, binds all countries to reduce the greenhouse gases emitted by them by 25 to 50%. This is an attempt to lower the global warming to less than 2 degrees Celsius by the year 2030. Buildings are an integral and elementary part of the global energy system. According to the United Nations, buildings use about 40% of the global energy, 25% of all global water, 40% of global resources, and they emit 1/3 of all greenhouse gases into the environment. For buildings to be able to realize their potential, they first and foremost must be energy efficient. According to LEED, 33 to 39% of a building's energy use is in the HVAC. Greenbuild estimates that 6% of all the world's energy is used just for cooling. As discovered in the Helsinki Report, which was a report that studied the chiller efficiency in 3 cities in Europe, and found that there's a wide gap between design efficiency and chiller plant efficiency in the real world. We're finding that the chiller plants are far from being energy efficient. They often suffer from a huge problem called low delta T syndrome. Research suggests that more than half of the buildings with a central plant are suffering from low delta T syndrome. Many experts think that this total could be much higher. Low delta T syndrome can occur in buildings for several reasons, 4 of which are coils and valves are not sized properly, too much water is delivered to the coil or the heat exchanger, coils follow and degrade with age or lack of proper maintenance, and water systems usually are not dynamically balanced. In order to dive deeper into how low delta T syndrome occurs, let's start with a few basic principles and examples. We'll start in the classroom on a quick lesson on power output. This formula is one you've probably all seen many times. For our example, Q is our load in BTU and is constant. Using the formula on a coil, flow and delta T are inversely proportional, which means as our flow, as we measure here in gallons per minute, increases, the delta T at our coil will decrease. Let's take a look at it actually on a graph. This is some actual data points from an air handler we have at MIT. The power output, as you can see in the graph, increases across the green line as the flow increases. When we add the delta T data points to the graph, we can see that the delta T decreases as the flow to low ratio decreases. What happens when our coil receives more flow than is needed? As the flow increases beyond 55 gallons per minute, as you can see on the bottom of the graph, the power curve begins to flatten. Then power output actually diminishes as the flow continues to rise. The coil is entering a point or an area that we call power saturation. This is a point where there's no more additional heat transfer available for the added flow through the coil. We can also mark this point as entering an area that we call the waste zone. A plant will operate in the waste zone with a higher flow but no additional BTUs. As you can see, we pump more water. Our delta T is reduced, and we do not add additional BTUs for the extra pumping or the additional flow. So basically, the waste zone represents all the additional water that a coil cannot use. This is the lost efficiency, lost money, or wasted resources. What's the cost of overflowing the coil? In this example from MIT, which shows actual data points, we picked 2 points on the curve to show the cost difference in pumping 2 different flows. Point 1 is a flow of 55 gallons per minute and equates to a 300 kBTU per hour rate of power. Point number 2 is a 65 gallon per minute flow through the same coil, which equates to a 325 kTBU per hour increase in energy. Let's go back to the classroom and let's see how that additional energy increase works for our pumping energy. This is a formula called the Pump Affinity Law. And what we do is we use these difference in flows to determine the amount of extra pumping horsepower that's necessary to provide the additional flow. Let's take the variables from our example and enter them into the equation. As we can see for point 1, we have our 320,000 BTUs at a flow of 55 gallons per minute. Point 2, which was 325,000 BTUs at 65 gallons per minute. We enter them into the pump affinity rule to determine the additional horsepower that's needed. Because of the cubed ratio of the pump affinity rule, we can find that a 1.6% increase in cooling results in a 65% increase in pumping energy. What this proves is operating in the waste zone can be very costly as we're pumping using extremely high pumping energy to produce very minimal additional heat transfer. We see that low delta T wastes energy at the coil, but what effect can this have on the chiller plant? Chiller plants can be designed to be very efficient at the proper delta T, but low delta T can play havoc, often resulting in improper staging. Just like the coil, at the chiller, the flow and delta T are inversely proportional. As you can see here, once again, as our flow increases, our delta T will decrease. A simple example of improper staging of chillers due to low delta T. For this example, we would have a 1,000-ton chiller plant with 2 500-ton water-cooled chillers. Our design delta T is 12, and our maximum flow at each chiller is 1,000 GPMs. At design delta T of one chiller, a design delta T of 12, one chiller is able to meet the load and run at a maximum efficiency, as you can see in this example. What would happen to our chiller plant if our delta T would be 8 instead of 12? Using the same formula, we can see that we need to stage a second chiller due to the fact that we've increased our flow from 1,000 GPM to 1,500 GPM. So in order to maintain the same 500-ton load, a second chiller will need to be staged due to additional flow, not because of additional demand for cooling, but because we're flowing far too much water through the system. Running extra chillers and pumps when not necessary are common problems with buildings that suffer from low delta T syndrome. With those examples in mind, we can conclude that if the delta T could be maintained as designed, the central plant would operate much more efficiently. And I'm going to show you a product that you can use to enact this. The Belimo Energy Valve manages delta T and can help solve low delta T syndrome. The Energy Valve, through its delta T manager software, can be set to maintain a desired delta T set point. The Energy Valve has the built-in flow meter, 2 temperature sensors to monitor and maintain flow. If we take a look again at the example we used from MIT, we can eliminate the extra flow in the waste zone by setting a delta T manager to limit the delta T to 12 degrees. By setting this delta T at 12, we're able to reduce the extra flow from 65 to 55 GPM, as the Energy Valve realizes the delta T is dropping below set point and reduces flow through the coil, eliminating the waste zone or all the additional flow beyond 55 gallons per minute. Another example of the Energy Valve's functionality. This is actual test data from a technology site in the southern United States. The Energy Valve was installed on an air handler to determine the effectiveness of our technology. The graph shows 3 large plots of data points. The bottom points you see with the line going through them is with the Energy Valve working as a pressure-dependent valve. So basically what we were doing is we were able to turn the functionality of the Energy Valve off, including the delta T manager and the flow control technology, to make the valve behave as a regular pressure-dependent control valve. The only functionality enabled was the modulating control function. When we ran the valve, we were able to maintain a 60-ton load through the unit at an average flow of 240 GPM. You can see there are many plots along this axis, but the average amount of flow needed was 240 GPM. Next, we turned on the feature of the Energy Valve, making it a pressure-independent valve. We used the flow meter along with the analog control signal to keep the flow constant instead of allowing overflow based on set point. When we enacted the pressure-independent feature of the Energy Valve, we were able to maintain the same 60-ton load with a reduced flow of 144 GPM. Then finally, in the same air handling unit in the same building, we turned on the delta T management feature of the Energy Valve. We set a delta T for a 15-degree set point, and we're able to reduce the flow to maintain the same 60-ton load all the way down to 96 GPM. This is a savings of 60% less flow while maintaining the load and increasing the delta T. So these are a couple examples, but now I'll show you a couple great case studies that we've done with Energy Valves. The first case study was at the Massachusetts Institute of Technology. This was one of our first Energy Valve customers and one of our biggest success stories to date. At Massachusetts Institute of Technology Hayden Library, we were able to take the delta T across the 6 air handling units from 6 degrees Fahrenheit to 12 degrees Fahrenheit, thereby reducing the water flow by 49%. An independent energy company did analysis on the work we did in the Hayden Library and estimated that if these actions were taken across the entire chilled water plant through the entire campus, their annual energy savings would reach up to $1.5 million. There's a white paper available for this case study on energyvalve.com if anyone is interested in looking at this further. Another case study in a different part of the world was in Singapore at the Nanyang Technical University. Here we were able to reduce the chill water flow through the building by 18.5%, saving them an average of 175 to 220 kWh in annual cooling energy. Another amazing success story. To achieve a higher energy efficiency in buildings, a change of mindset is needed. A building revolution needs to be made to meet the requirements from the Paris Protocol and the Helsinki Report. Closing the performance gap of central plants will lead to demanded energy efficient usage. The introduction of the Energy Valve 3.0 will create advanced efficiency, automatic optimization, and cloud-based services. For more information on energy valves and how they can help you fight low delta T syndrome, please contact Belimo or visit energyvalve.com.
Thank you so much, John. It looks like we have a couple of questions coming through. So if anyone has joined us partway through the webinar, be advised that this webinar is being recorded and will be posted to different marketing websites associated with Belimo at a later time. Right now, this is the question and answer session. So if you have additional questions or if you have any questions, please feel free to type those questions into the question box. I will read them aloud and John will answer them appropriately. John, are you ready?
I hope I'm ready.
Okay, sounds good. So our first question is, this individual wants you to just give a brief overview of what exactly the delta T syndrome is.
Oh, okay. I guess I can start out by a definition of low delta T syndrome. You know, my definition of it is the problems which occur in a building due to ineffective heat transfer, which is caused by flowing more water than the desired load demands. So basically, low delta T syndrome is all the problems that happen in a building because we flow too much water.
Okay. That kind of answers the second question. What are the major causes of low delta T?
Yep, so those are some of the ones we covered, but they can range anything from valves, which are oversized, control or coils, which are basically sized for a design load. We typically don't hydronically dynamically balance our systems. We balance them at a static set point, which can lead to some differential pressure issues. Also, coils can degrade, get dirty, foul up, get dusty, the filters aren't changed. All these issues can cause low delta T syndrome in buildings.
Okay. What was the size in tons of the Nanyang chiller plant in Singapore?
That is a really good question. I would have to actually look into the case study to tell you that, but we can certainly pull that up, and whoever asked that question, we can send them a copy of the case study. It is on our website. Sounds great.
Next question, can we use the energy valve to control with flow of FAHU without the need of a two-way valve? Hope I read that right.
Maybe they're saying without the need of a three-way valve. I'm not sure exactly how to answer that question.
As a follow-up question to that, what is the smallest and biggest size available for the energy valve?
We have energy valves that range from the size of a 1/2 inch or DN15 all the way up to 6 inch with a flow of 713 gallons per minute.
Okay. Did the percentage savings calculations include the cost of installing the new valves?
Yes, they can. We do have a cost savings tool that's available on our website where you can actually enter the data that you would have as far as an expense for upgrading to an energy valve or changing your system to energy valves.
And that's also available on energyvalve.com as well as belimo.us. Next question. These valves can be used in water-cooled condenser chillers to control the condenser pressure?
They can control the flow, yes, and by being pressure independent, we can keep the pressure at a certain level, but we don't have pressure control for the valves.
Was the system at MIT provided with VFD chiller pumps? Would MIT see much greater savings with VFD-controlled pumps?
I do not have the exact answer to that question. I believe that they have VFD pumps installed. Energy valves work very effectively in conjunction with VFD. Being able to vary the flow is very important to controlling the low delta T.
Can the energy valve replace control valves of a FAHU?
Yes.
Okay. Can we replace the BTU meters for energy valves?
Can you replace BTU meters with energy valves?
For the energy valves.
Certainly. The energy valve also acts as a BTU meter. So in effect, you could replace BTU meters and a control valve with an energy valve.
Next question. How is the system to be water balanced after the energy saving valves have been installed?
Yeah, once again, I'm not exactly sure what that question means. Once energy valves are installed, your system is in effect dynamically balanced, working at basically a valve authority of 1. Since the valves are pressure independent, you don't need to use circuit setters or any type of manual balancing valves on the coils. You may have them in a headers to control flow to a floor or something like this, but you wouldn't need to have any type of manual circuit setters.
Okay, and this is the follow-up to the question you just answered, John. Can the GPM be read directly from the energy valve?
Yes.
Can you control the delta T by knowing the size and type of coil and integrating into the control equation?
Yes, absolutely.
Can we use the energy valve across the chiller inlet outlet to increase delta T in production?
Across the chiller inlet and outlet. I don't know necessarily that you would want to install it on the inlet and the outlet. You could certainly use it on one side of the chiller.
Okay. And it looks like we might have one more question coming in. Water balancing is specified to be performed for most projects. Should we balance units with energy valves at their full flow rate?
Yes, I mean, initially you're going to probably balance the energy valve at the full flow rate. Absolutely.
Last question, and then unfortunately we're going to have to conclude this webinar. Is there maintenance and availability information available for these valves?
That was maintenance and what?
And availability information available for these valves?
Well, absolutely. The valves themselves are not a maintenance product. And energy valves are available now. The new version of the energy valve, version 3, will be available next month, which will add some great new features to the valves. But But yeah, you can order energy valves today.
Okay, I know I said last question, but I just had a couple more come through.
Okay.
Just confirmation, can we use the energy valve on a chiller?
Yes.
Okay.
Granted that the flows are matching.
All right. Well, John, I want to thank you so much for giving us this excellent presentation. I also want to thank everyone who participated in today's webinar. If we did not get to your question or we told you we would answer your questions, we will get you the correct answer shortly. Please be advised we have another webinar next month, and it's going to be on the unrivaled butterfly valve technology for HVAC applications, and that's going to be on the 22nd of March. So thank you everyone for taking the time to participate in this webinar. I hope you have a great day. Thank you.